Imagine being able to repair and replace human body parts in the same way we do with car parts. This may sound like pure science fiction, but scientists are exploring new medical technologies that could allow them to grow custom-made and ready-to-use organs. This means diseases like leukemia, Parkinson's, diabetes, heart diseases, and strokes could all be reversed and cured with bioengineered organs. These lab-grown organs would be made from stem cells. So what are stem cells and where do they come from? Stem cells are special human cells that act as a repair system for our bodies and are able to fix damaged tissues. They are able to develop into many different types of cells, like muscle cells or brain cells. All the cells in our bodies are believed to originate from stem cells. As they mature, they then obtain their functions and become what is scientifically referred to as differentiated cells. Stem cells are divided into two main forms: embryonic stem cells and adult stem cells. Embryonic stem cells are cells found only in very early development and are the precursors to every cell type in the human body. They have an amazing potential to turn into almost any body part. They are also virtually immortal and are able to produce new cells even after months in a petri dish. Some embryonic stem cells used in research today come from unused embryos during an in vitro fertilization procedure. These unused embryos are instead donated to science. Other embryonic stem cells can be created in the lab using genetic reprogramming. Adult stem cells, on the other hand, are rare cells found in the body after its birth and throughout its life. They reside in tissues like the brain, the bone marrow, the blood vessels, the muscles, the liver, and the skin. Adult stem cells wake up when the tissue needs to be repaired because of certain damage or disease. Scientists have been able to harvest stem cells. They were also able to make them from differentiated cells by reprogramming them back to a stem cell state. However, these cells so far are flawed and can only develop into a small number of cell types. Out of the many possibilities to use stem cells, tissue regeneration is the most essential. Currently, the world is facing an organ shortage crisis. In the US alone, more than 100,000 people are on a waiting list for an organ transplant. Being able to bioengineer and grow organs from stem cells would largely help with this problem. At the same time, these organs would be custom-made and ready to use. They would be generated from the patient's own stem cells, which would greatly reduce the risk of the body's immune system rejecting the transplant. Scientists could go on to cure heart diseases or diabetes. Special cells made from stem cells could be implanted into the heart or the pancreas, where they could replace non-functional cells. Even brain diseases like Alzheimer's or Parkinson's could be cured by repopulating the brain with healthy cells. These scientific achievements are yet to be accomplished for regenerative medicine. The techniques are still far from perfect, but scientists are still researching and working on new ways to harness the power of stem cells. They believe that in a few years from now, regenerative medicine will be available and a preferred method for everybody. What do you think of stem cell research? And what do you imagine the future of stem cell therapy could look like? Share your thoughts in the comment section.
Mechanism of action of cell-based therapies. Stem cells are self-renewing undifferentiated cells that can have the potential to differentiate into any organ-specific cell, depending on their origin. They can be characterized as either embryonic or somatic or adult stem cells. They differ in their potency and differentiation capacity depending on the tissue of origin. Thus far, hematopoietic stem cells, or HSCs, and mesenchymal stem cells, or MSCs, have emerged as promising cell-based therapies for severe refractory IBD cases. HSCs can be isolated from the bone marrow, umbilical cord blood, or more commonly peripheral blood of an individual and eventually transplanted back to the same individual, autologous. These stem cells can also be received from a matched donor, allogenic, for potential cell-based therapy. HSCs are progenitors of both the myeloid lineage, monocytes, erythrocytes, macrophages, neutrophils, and dendritic cells, and the lymphoid lineage, T cells, B cells, and natural killer cells, and are capable of migrating to damaged tissue and differentiate into immunomodulatory cells in order to restore normal gut mucosal barrier function and reduce inflammation. Like HSCs, MSCs are also multipotent self-renewing cells that are capable of differentiating into several types of cells and are present in various tissues of the body. MSCs can be isolated for clinical application from bone marrow, umbilical cord blood and tissue, Wharton's jelly, or adipose tissue. MSCs derived from adipose tissue are easily extracted in large quantities with reduced morbidity and discomfort for the donor. The underlying immunomodulating mechanisms of MSCs are still unclear. However, studies have reported that MSCs exert their influence on the target cell by associating with them in a close proximity, and not solely via cell-to-cell contact signaling. Due to their low immunogenicity, MSCs have certain advantages over HSCs in regards to therapeutic transplantation. This property stems from their low expression of MHC1 cell surface proteins, as well as a lack of MHC2 and co-stimulatory proteins. As such, the need for chemotherapy in MSC transplantation is eliminated, whereas it is necessary in HSC transplantation. Another benefit is that unmatched allogeneic MSCs can be utilized in the transplantation procedure. MSCs also offer an advantage to mid-sized transplant centers as they can be mass manufactured more readily. Both HSCs and MSCs have immunomodulatory effects that can downregulate mucosal immune reactivity and promote tissue healing. Indeed, HSCs and MSCs have emerged as a promising therapeutic option for severe refractory Crohn's disease cases, such as refractory fistulizing perianal Crohn's disease. In perianal Crohn's disease, the objective is to deposit MSCs locally in fistulizing tracts to downregulate the local immune response and promote wound healing. However, future studies are necessary to fully decipher their complex cellular mechanisms. Cellular therapies will not be limited to HSCs or MSCs. Other cellular therapies, such as induced pluripotent stem cells or iPSCs, will also likely be explored in preclinical settings. Importantly, future studies should include assessments of long-term safety, the duration of response, and the cost-effectiveness and technical feasibility of such cell-based therapies.